Welcome to video 3 of 5 The Crown Jewels or Linear Algebra. 3 legendary techniques await: Eigen decomposition, where matrices reveal their secret directions; singular value decomposition, a tool that works on A and Y matrix and once won the Netflix prize; and principal component analysis PCA, the 4-step recipe that compresses data while keeping what matters. This is the video where everything from part 2 pays off. Let's go! Now we arrive at one of the most beautiful ideas in all of mathematics: eigenvalves and eigenvectors. Now I want to give you the intuition before the formula. Remember our idea that a matrix is a machine that transforms vectors. Normally, when the machine runs, a vector's length and direction both change. But some special vectors refuse to turn. The transformation only stretches them, or shrinks them. Their direction survives untouched. Those stubborn vectors are the eigenvectors. And the stretch factor, how much each one grows or shrinks, is its eigenvalue, lambda. Here's the best picture I know. Spin a globe. Every city on Earth moves, except the axis through the poles. That axis is the rotation's eigenvector, and since its length doesn't change, its eigenvalue is 1. The defining equation on the slide says exactly this. A times v equals lambda times v. Applying the whole matrix to v is the same as simply scaling v by a number. Eigen is German for OW, and these are the matrix's own private directions. Once you have the eigenvectors and eigenvalves, something remarkable becomes possible. You can take the matrix apart. This is Eigen decomposition. The formula: A equals P times D times P inverse. 3 pieces. P is the matrix whose columns are the eigenvectors. D is diagonal, holding the eigenvalves. And P inverse changes us back. Here's how to read that formula right to left, like a story. P inverse translates us into the eigenvector coordinate system. The A diagonal matrix does simple and dependent stretches along each axis. And P translates back. So every diagonalizable matrix is secretly just stretching, viewed from the right angle. That's a stunning fact. The fine print for the exam: this only works if A is square and has enough linearly independent eigenvectors. And why bother? Try computing A to the power 100 directly. Brutal. But PD to the 100 P inverse. Powering a diagonal matrix is trivial. That's how Markov chain simulations leap 100 steps in one bound. Enough theory, let's compute one by hand together. Take the matrix 4, 1 on the top row, 2, 3 on the bottom. Step 1: the characteristic equation, determinant of A minus lambda I equals 0. We subtract lambda from the diagonal and take the determinant. Step 2: expand it. 4 minus lambda times 3 minus lambda minus 2. Multiply out. Lambda squared minus 7 lambda plus 10 equals 0. Step 3: factor. Lambda minus 5 times lambda minus 2. So our eigenvalves are 5 and 2. Step 4: for each eigenvalue, solve for its vector. Lambda 5 gives the vector 1, 1. Lambda 2 gives 1 minus 2. And now always verify. A times 1, 1 gives 5, 5, which is 5 times 1, 1. It works. Before you go, 2 magic shortcuts. The trace, the diagonal sum, 4 plus 3, 7 always equals the sum of eigenvalves 5 plus 2. And the determinant 10 equals their product. Free sanity checks and instant answers on multiple choice questions. Eigen decomposition has one frustrating limitation: it demands the square well-behaved matrix. But real data matrices are rectangular. 1,000 customers buy 20 features. So what do? Enter the singular value decomposition SVD, which works for absolutely A and Y matrix. No exceptions. That's why it's called the crown jewel or linear algebra. The formula: A equals U times sigma times V transpose. And the geometric reading is gorgeous. A and Y matrix, any transformation at all is just a rotation, then a stretch along the axes, then another rotation. Rotate, stretch, rotate. Even the messiest transformation decomposes into those 3 clean moves. The cast or characters U and V are orthogonal matrices. Remember them from the zoo. Pure rotations. U comes from the eigenvectors of A transpose, V from A transpose A, and sigma holds the singular values sorted from largest to smallest, each one telling you how much energy its direction carries. That sorting biggest first is about to become very profitable. So what do you actually deal with an SVD? Here's the highlight reel: 1D composition, 6 superpowers. One-dimensionality reduction: keep only the directions with large singular values and the data shrinks while keeping its important structure. 2. Matrix approximation: truncating small singular values gives the best possible low-rank approximation. That's a theorem, not a hope. 3. The pseudo-inverse: an inverse for matrices that technically don't have one. Keep that in your pocket for least squares at the end of this unit. 4. PCA: the singular vectors literally are the principal components. 5. Image compression. Here's the arithmetic: a 512 by 512 image holds over 260,000 numbers. Keep just the top 50 components and you store about 50,000 5 times smaller and your eye can barely tell. And 6. My favorite story: the $1 million Netflix prize was won with SVD style factorization of the users by movies rating matrix. This math literally pays. And now the grand finale of our linear algebra chapter: principal component analysis. PCA. PCA is a dimensionality reduction technique. In plain words, it shrinks the number of features in your dataset while keeping the most important information. It does this by transforming correlated features into a smaller set of uncorrelated components. Let's define those words properly. Correlated means two things move together. If one rises, the other tends to rise or fall, predictably. Uncorrelated means no relationship. The source book has a lovely example: shoe size and exam marks. Big shoes do not mean high marks. Uncorrelated. Why do we want this? Picture a housing dataset with area in square meters and area in square feet. 100% correlated, pure redundancy. One of them is dead weight. PCA automatically merges overlapping features like that. The benefits: less redundancy, faster computation, easier visualization. Now let me show you how it pulls this off. Before the 4-step recipe, I want to give you the intuition, because once you see what PCA does, the math becomes obvious. Imagine your data as a messy cloud of points like stars scattered in the sky. PCA's job is to find the most revealing angles to view that cloud from, so you don't miss the big patterns. Here's a physical demo you can do right now. Hold up a pen, photograph it from the side, you see its full length. Now photograph it and on it looks like a dot. Same pen, but one viewing angle preserves the information, the other destroys it. PCA automatically finds the side on view. The direction of maximum spread, maximum variance, becomes principal component 1. Then, at exactly 90 degrees to it, the next best direction, component 2. That right angle guarantees the new features don't duplicate each other. That's the uncorrelated promise kept by geometry. Keep the top few components, drop the rest, noise removed, dimensions reduced, story intact. One-line summary: from the source itself, PCA keeps the most informative directions and removes the redundant ones. Here is the entire PCA recipe, 4 steps, and I promise every PCA ever computed, from Excel to scikit-learn, is exactly this pipeline. Step 1: standardize the data, put every feature on a fair, comparable scale. Step 2: compute the covariance matrix, measure how the features vary together. Step 3: Eigen solve that matrix. The eigenvectors give the directions, the eigenvals give each direction's importance. Step 4: project, keep the top components and transform the data. Now pause and look at what just happened. Matrices, symmetric matrices, Eigen decomposition, variance, everything we've built in this chapter converges right here, inside one algorithm. PCA is literally the Eigen decomposition of the covariance matrix. Say the 4 verbs with me: standardize, covariance, eigensolve, project. Now let's zoom into each step. Step 1: standardize. And let me convince you, it's not optional. Different features live on wildly different scales. Salary measured in tens or thousands, age measured in tens. Now remember, PCA hunts for directions of maximum variance. Salary's raw variance is astronomically larger than age's purely because of its units. Skip this step, and PCA just points at salary and says done. Meaningless. The fix is the z-score on the slide. Subtract each feature's mean, divide by its standard deviation. After this, every feature has mean 0 and standard deviation 1. Everyone competes fairly. A quick example so it sticks. Age 40, when the average is 30 and the deviation is 5, Z equals 40 minus 30 over 5 plus 2. Read it as 2 standard deviations above average. And notice the units vanished. Z scores are pure numbers, so salary and age can finally be compared apples to apples. Step 2. With everything standardized, we compute the covariance matrix, the table, or how features vary together. The formula for a pair of features reads like a recipe: multiply the two features' deviations from their means average over the data. If both features tend to be above average together, positive products, positive covariance. If one is up while the other is down, negative, around 0. No linear relationship. For a dataset with, say, height, weight and exam score, we get a 3 by 3 matrix. Height and weight, large positive entry. Height and exam score, about 0 as you'd hope. 2 structural facts to notice. The diagonal holds each feature's own variance covariance with itself. And the matrix is symmetric: covariance of A with letter B equals covariance of B with A. Remember our zoo. Symmetric matrices are the well-behaved ones, always diagonalizable, with orthogonal eigenvectors. That's precisely what step 3 is counting on. Step 3, the heart of the algorithm. And here comes the punchline of the whole chapter. We take the covariance matrix and solve. Ax equals lambda x, the same Eigen equation from a few slides ago. The eigenvectors of the covariance matrix are the principal components, the new axes. And the eigenvalues tell us how much variance, how much information each axis captures. PC1 is the direction of maximum variance. PC2 is the next best, forced to be perpendicular to the first. And because the covariance matrix is symmetric, that perpendicularity comes free. The mathematics keeps the 90-degree promise all by itself. Here's a computation examiners love. Suppose the eigenvalues are 4.2, 1.1, 0.4, and 0.3. What fraction does PC1 explain? 4.2 divided by 3 total 6, 70%. One direction carries 70%, or everything the data has to say. And step 4, cache in. Sort the eigenvalues in descending order. Select the top k components, typically enough to capture 95% of the total variance. Then project the original data onto those k directions. The projection itself is just one matrix multiplication, the operation you mastered at the start of this chapter. What do you get? Fewer dimensions, faster models, less noise, with the important patterns preserved. A real number to hold on to. The classic MNIST handwritten digits dataset has 784 pixel features. Around 150 principal components retain 95% or its variance. That's a 5x compression before any model even starts training. And what about the 5% we threw away? Mostly noise. That's why PCA often makes downstream models more accurate, not less. You're feeding them signal minus the static. Let's read an actual PCA picture together, because interpreting these plots is a skill of its own. The dataset has two features: radius and area, the black axes. Since area grows with radius pi r squared, they're strongly correlated and the data cloud forms a tilted ellipse. PCA finds two new directions. PC1 runs along the long axis of the ellipse, the direction of maximum variance, holding most of the information. PC2 sits at 90 degrees along the short axis, capturing the little that remains. Now the punchline: the spread along PC1 is huge, along PC2 tiny. So we project every point onto PC1 and our 2D dataset becomes 1D, keeping most of the structure. Compression achieved. One last question worth chewing on: when would PCA not help? When the features are already uncorrelated. A perfectly round cloud has no preferred direction, every angle is equally boring. PCA thrives on correlation, no correlation, nothing to squeeze. Quiz 3 and S1 checks the deepest connection in the chapter. In PCA, the principal components are obtained from which mathematical objects? Option A, the singular values or the standardized data. Option B, the eigenvectors of the covariance matrix. Option C, the inverse of the covariance matrix. Option D, the determinant of the data matrix. Think back to the 4-step pipeline: standardize, covariance, eigen, solve, project. Which step made the components and what exactly did it produce? Pause the video and commit to an answer. The answer is B, the eigenvectors of the covariance matrix. That's the very definition of PCA. Eigen decompose the covariance matrix. Eigenvectors give the directions, the components themselves, and eigenvals give their importance, c, the variance each captures. Now if you picked A, I actually want to congratulate you, you were half right, and it's a subtle miss. PCA can be computed through the SVD of the standardized data. But the components are the singular vectors, not the singular values. Vectors are directions, values are magnitudes. Examiners adore that distinction. The inverse and the determinant play no role at all. And one bonus question to test yourself: why are the eigenvectors guaranteed orthogonal? Because the covariance matrix is symmetric. The whole chapter in one answer. Linear algebra. Complete. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.